afternoon, students. So today we are going to this is actually third lecture regarding the band structure of 1D, 2D, and 3D materials. Okay. So what is the significance of band structure? That I don't need to discuss because we had a multiple discussion on it in the during the first semester courses. And one important thing that we must convince ourselves, like whatever calculation we are doing, whether it's a PN junction, BGT, transistor, whatever, we are starting from the band structure, right? And if we have a band structure, then it is a whole lot easy to calculate any parameters, okay? And this semester we have started a very general formula, right? And formula of current, that means if you have a piece of semiconductor, correct, and we need to apply some voltage or if current on this piece of semiconductor, we try to know that what is the output. Means if you apply voltage on piece of semiconductor, what is the current, okay, through this semiconductor. That's what we are interested. We have framed a particular expression, and once we frame the particular expression, we came to know that we need to have a proper knowledge of density of states. Now, if you want to have a density of states of a particular materials, I'm not calling it semiconductor, of a particular materials, then what we need to know? We have to solve Schrodinger equations, right? But before we solve Schrodinger equation, we really need to know what is the crystal structure of the semiconductor, whether it's a amorphous or crystalline, whatever. Okay, somehow if we know the crystal arrangement of this semiconductor, then we need to solve it for by the Schrodinger equation. Then we will get a eigenvalues. So this eigenvalues nothing but my energy levels. Okay, and this eigenvalues we are getting the function of momentum, that is k value. So that means we get to know about energy versus momentum, right? And last couple of lecture, what we did, we actually frame how to work out, how to get to know how to frame the EK relation, that is energy versus momentum relation, which is fundamental for any type of electrical characterization or even optical characterization also, or optical properties also. This EK diagram, and what we have to do here to find out EK diagram, and from there we have to apply a lot of theories on it, and we'll get to know all the parameters. Fine. Now the question is, last couple of lecture, which we are trying to see how to know EK diagram from the crystal structure, and we have applied lot of theories, lot of assumption, and try to solve a complicated crystal. Solve means we need to solve Schrodinger equation on this complicated crystal. And first we have started with the proper Schrodinger equations. Then we just we replace it to a particular basis function. Okay, and we saw that we can easily get EK diagram of a one-dimensional lattice nicely. We can get EK diagram of two-dimensional lattice nicely, and three-dimensional as well. But there are some modification we have done, that is we have also converted. We are not actually directly solving in a matrix expression. What we are doing, we are somehow converted it to kind of summation expression, the matrix expression to summation expression, and we did something so that we can easily get EK diagram almost analytically, not through a computer. We get that expression. Now the question is, just look at this complicated silicon this is germanium band structure, this is silicon band structure, and this is gallium arsenide band structure. You know that these all are actually well-known semiconductor in the history of semiconductor devices. But if you carefully see that, you know that silicon is most popular one, I guess. So you say that you have a conduction band, we have a Sorry, this is conduction band, valence band, and this is actually EG, band gap. Can you just check? This is my valence band, this is my conduction band, right? Conduction band bottom and valence band top. This is EG. But now the question is, whatever solution we did, whatever, we have not encountered such a complicated band structure. Now, why we are lacking? Why we are not getting? Because we have solved even 2D and 3D. The thing is that, remember, suppose you have what we have done, that at the moment we have assumed that we have a one dimensional crystal lattice or two dimensional crystal lattice, whatever, okay, or three dimensional, whatever, and each atom is associated one basis function, that is 1s, suppose. That means it is like we have done unknowingly or knowingly that one dimension of hydrogen crystal, or two dimension of hydrogen crystal, or three dimension of hydrogen crystal. But hydrogen has a one benefit, one electron, one nucleus. No, so one electron means you can somehow manage it by 1s. That is basis function of s. But suppose we are going very complicated band structure like silicon, like germanium, like gallium arsenide, like helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So it's not restricted with only it's a multiple electrons, and it is not restricted only s orbit. It may have a other orbit like s, p, d, f, all type of. So suppose it means that, suppose you have atoms, okay, and the basis function may not be 1. It might have a s, p, d, or pd, or sp. You might have had the sp hybridization, all these things that you know, spd, sp2, all kind of hybridization. That means it's not restricted to only s. It might have as, p, d, all kind of basis function. That means you have a one single atom, but instead of only s, we might have s, p, d. That means you have a SPD, all kind of bands basis function, and the moment you have a more and more basis function, you will get more and more this band. These are the band. These are the band. You will get more. So I'm not telling about the subband. Subband is a different physics. I'll tell you later. But what about the major band we are getting is corresponding to different basis function, and that is very important, right? And how to so this is kind of, you know, that orbital like ASP. This is a different p orbital. S is actually kind of symmetry. P is usually it's not symmetry. So px, py, pz, similarly d orbital, f orbital, all kind of orbits are there. And based on your problem, we have to choose what are the basis functions. Very important, and definitely you don't need to, because most of our semiconductor experience means, I mean to say, we already formulated last 100 years, like last 100 people have developed what kind of basis function we need to consider for to solve a particular semiconductor, more or less. I'm not saying it is perfect, but more or less people have nice knowledge on it. So you can choose a particular basis function, and over that you can start. Okay, that's the idea. Now before I start, let me, because when we have started that principle, periodic lattice first semester, I told you that particular concept called unit cell, that you can remember, and this is very unique here because we need to consider those unit cell concept here also. One is actually, suppose it's a two-dimensional periodic crystal, okay, periodic, and so one unit cell you can think about. This is called one unit. What does it mean, one unit? So you can repeat this unit. Still it is, you can repeat this unit, this brown unit. Still it is actually kind of periodic. Like, so if you replace this one by this one, the properties will be the same. So instead of this one, if you can consider such a things over, then it is the properties of this one and properties of this one be the perfect same. So that's what I'm saying. So this is another kind of unit cell. Similarly, this is also kind of units, another kind of unit cell. Thing is that the properties, how these things are adjoined. So this unit cell properties is particularly same of this unit cell. So that means it's kind of periodic unit cell structure, correct? Like that. And one is actually trivial answer, that is one atom, one unit cell, right? That is also there. And this is another kind of thing. So why I'm showing it in, that will clear in a minute. So that also you can consider, instead of, so here we have considered 4 as a unit cell, you have considered 1 2 3 4 5 6 7 9 as a unit cell, but it's not a great idea to consider those things. Sometimes I saw that people also consider these things. Okay. Now, how to find out primitive cells? So this weakness is algorithm. You already know. This is actually you have to consider one particular point. Then you have to draw a line to a nearest neighbor. Okay. Then you have to do bisection of that, and the area, uniform area, is actually called the primitive cell. Okay, fine. Now, here I also told that day, like called a Bravia lattice concept. No, like if if it is like Bravia, Bravia, so lattice concept. So if you start from here, okay, and if you want to go reach over there, so you can have an integer of particular distance, like from here to here. Suppose it may be how much a. So if you multiply it with a particular integer, you will reach over here. Then if you multiply with particular integer, you will reach over there. So you can reach any point over here, any direction over there with a particular formula. This formula. No, we had a discussion on it. Now, this is a kind of great example of non-Bravia lattice. So you see, the red ion is a different. So what is actually periodic crystal? Periodic crystals means, like, if you go any point of this two-dimensional picture and the surrounding is same, right? Similarly, if you go any point, the surrounding is same, correct? But here, if you go to the red point, surrounding is not the same. Correct. This point and this point is totally different. So if you go, the surrounding is totally different. If you go to the another light blue color point, no, so the surrounding is totally different. Similarly, if you go to the red, surrounding is totally different than if you come to the light blue color. So surroundings are totally different. So it is not at all a non-Bravia lattice. Now, how to make it Bravia lattice? So that day we have to consider, like, you just consider two things as a single unit, and if you represent, so this thing, this thing, this thing, if you represent this thing single unit by a black dot, then it is kind of Bravia lattice with basis function, right? How they link to SPD, whatever. So this is kind of concept, and this concept we have to introduce our knowledge to find out decay diagram, and then we'll complete it. So let's start. So principle of Bandstructure, multiple basis functions. So multiple basis, one thing it's very important, like suppose what we had a discussion, suppose you have a n number of atoms, like, so how many solution you are expecting? Suppose one dimension crystals and you have a n number of atoms. So how many solution you are expecting? Eigenvalues n. But if you have a two number of basis functions, so how many solution we are expecting? 2n. If you have a 5 number of basis function, because SP, DF, whatever, how many number of solution? 5n. That means if you have a B number, B is for basis or whatever, if you have a B number of basis function, how many solution you are expecting? NB. So now it's very, very complicated. It's not about the total n numbers, so you'll get a NB number. Solution may be n, but you need to, actually, what I'm trying to tell that you have to solve the Hamiltonian matrix, H matrix. So what is the, it's not at how many solutions. Solution would be n, okay, that's, or nb, whatever. But how many? So what is the dimension of the matrix? Dimension of the matrix is nb cross nb. Huge. So it's practically impossible to solve in a computer. So, right. So that is so how to avoid these things. Okay. So that is the discussion here. So suppose I have taken only one dimensional array instead of two dimensional. Two dimensional would be your homework. So one dimension I have taken and I have named it. One is A, another one is B. So this is actually A and this is actually B. Similarly, I have named all these atoms. Okay, so this is A, this is. Similarly, another thing is that we have to see what is the interaction matrix. What is the interaction component? So I say A and B relates with that T. And how to find out T? We already had a discussion on it. Similarly, how my B actually relates to A of next one, not this one. B relates to A of next one, suppose I represent by T1. Okay. Now, if someone asks me to form the matrix, to write the matrix, okay, so it is easy to write. Like, you start anywhere, suppose this is my part. Okay, so let us see how it looks. So, what is the diagonal part? Diagonal part is always, as you know, that's always my same. Diagonal matrix would be the same. Now, this A, so suppose let me write some number. I think for 1, 2, 3. So suppose this is my N1. Sorry. This is my N1. This is my 3, like that, huh? So 1, 2, 3. So like H11. So that is actually, you know, epsilon. Now what is the component of H12? So H12. So H1. This is 2. So H12. As we know that we already mark H12 is related by this one, relates to this one. It's actually T. You already mark it. So we put it as a T. Right. Similarly, H13. So H1 related to 3. Now you see H1 here and 3 is here. It is far away from each other. So definitely the contribution is 0 here. H matrix contribution of particular component is 0 because the wave function is far away from each other. Even whatever the basis function, it is far away from each other. So this is I have put 0. Similarly, H14, so far away from that, that is also 0. But what is H23? H23, like this is from here to here, we have marked it as a T1. So H2, this one, 2, 3. This one I have marked as T1. So this is also kind of, you can write 0, you can write 0 over here. Similarly, I think similarly 3, 1, this is 3 and this is 1. So same thing, it is 0. This is 0. Right. So this kind of matrix we already dealt, no? So you know how to write. One important part that I would like to mention, like it's very important to, this is what, no, some mistake is there. 3, 3, this one, sorry. Just check carefully. 4 4 should be epsilon. Similarly, okay, let us remove all these things for clarity. Okay, so you already know that diagonal should be the matrix. So similarly, 5 5. So here actually, okay, this is my diagonal component. So please recheck it. Now, what is the component over here? So 3 to 4, 3 to 4 means here. So that is also T. This is T. Like that. So everything is more or less same. So this is C. Now what is important here? Why I am just group it here? So it is like that. You see this block. So just we have formed. So this is my epsilon. Okay. What is important here? So you have the diagonal matrix, that is fine, and we have already computed the component of one h12, h13, h14 and all these components. Now if you just box it, this box, and sorry, this box, so this is blue box. So at the moment please don't consider this one. So I'm talking about this box and this box. You see these components are repeating. So from this one, epsilon t, t epsilon, similarly, this is also repeating, epsilon t, t epsilon. Similarly, here also we'll have the same thing, epsilon t, t epsilon. That means these blocks are repeating. That's the beauty of this thing. That means even if you have a kind of a non-Bravia lattice, if you make a unit cell of light kind of thing, so what is good to know that instead of repeating the each and every component, what happened to simple hydrogen like atoms where each one is separated with this similar distance, perfect periodic crystal, no need to form the unit cell like a case of hydrogen. You see that you won't face such kind of things, but here you see that this block is repeating. So that's a good advantage. Similarly, you see this one and this one, how it relates to each other, this one and these things. So transpose of this matrix. So this one is the transport of this one, or this one is the transport of this one. So as a Hermitian matrix properties like this one conjugate transports, but fine because both are real, so we can T1 maybe. But important part is the transports of the matrix. So the main observation is here, like these blocks are repeating. Okay. So if somehow we can capture these things, then we are done. Similarly, these blocks is nothing but transports. Like so transport of the matrix. So that's the idea. So please remember those things. Okay. I'll refer it immediately after few slides. Now we come back to our original method. We have Schrodinger-Wave expressions. E phi is equal to H phi, and then what is the now if you have a n number of atoms, that's what I'm telling. Now it should be clear now. If you have a n number of atoms and you have a b number of bases, so how many, what is the dimension of H matrix? And that's what we can nb by nb, right? Now what is our idea? Idea is like that you have a matrix expression that needs to be converted to the summation expression, right? And for non-unit cell 1D crystal, like how we have done E phi n, H n m phi n. Remember last time what we have done, this is a simple expression which convert matrix expression to summation expression. But last time what happened? Last time is all actually periodic crystal, right? And we don't need to consider any unit cell over there, like, but here actually, here you see we need to consider unit cell. So this is actually one unit, this is one, like that. Okay, so here, and the most important part is that last time we have not considered any basis function. Since we have not considered any basis function, so this expression is quite quite okay, quite compatible. Okay, just let me correct it. We have considered the last time we have considered basis function like one atom, one basis. It's not that I have not considered or we have not discussed anything about the basis function. It is kind of one atom and one basis function. So for that reason, actually, we are very good to, we can easily take this type of summation expression. Now we have introduced B number or multiple number of basis function. Okay, now how to modify such kind of expression? What else we have to do so that we can incorporate that B number of basis function? That if that part actually incorporated, the problems looks like same thing. Okay, we can easily solve it. So let's come. Okay, so don't be confused, it is very easy. So same statement, we have a Schrodinger wave expression E phi is equal to H phi. So what is the dimension of the matrix? Answer NB and NB. So that is total dimension of the matrix. So now here we have written previously we have converted the matrix to the nth summation form with single basis function. So E phi n. So phi n component, how to write? This is the right. Now since we have incorporated, we need to add the basis function. So what is the addition thing that we need to do? Now basis function means like here suppose one basis function. So here is actually the modified this expression, whatever expression is modified over here with another matrix. Now again, see, the thing is that we are really cannot avoid the matrix form. So we have tried to avoid matrix form, but still it is coming. Now here you see that you should come like suppose if in dimension is b cross 1. Similarly, we have summation. Okay, so but the matrix dimension here H and M like b cross b, suppose, and phi and b. So what it tells you, like you just see, suppose you have one basis function. So that means E phi n b would be 1. So 1 cross 1 means one component, right? So if phi 1 is one component, and since we have considered one basis function, so b would be 1 and b is actually 1, so 1 cross 1, so that means h and m only, and 5. So that means if we have one basis function, which we have done last time, we did several examples last time. So that time what we have considered one basis function, and you see if you put b is equal to 1, you exactly come back this expression, right? So it is kind of more general expression, like, right? Again I'm telling you, so last time what we did, so this expression what I am marking by cursor, this is actually called expression with single basis function, correct? Now this is my general expression, and how to come back from here to here. So sorry, so it is very easy, like if you consider b is equal to 1, you see this is actually column matrix. Okay, now b is equal to 1 means 1 cross 1, that is single component, that is E phi n. Similarly h and m b cross 1, if it is a single basis function, so 1 cross 1 is a single component, like that, and phi n. So you see, like it is a kind of general expression which consider the number of basis function. Okay, now what next? The next is what is the general solution. So general solution C phi n b cross n, and same thing like what we have done last time. This is my general solution. Okay, and what we have to do, we have to put it back to the original expression, like this expression, and try to find out the overall expression. So if you put it back here, what you will get? You will get overall this expression, correct? Exactly the same way what we have done last time, and finally you get this one. Now you see E phi 0 b cross n, mk phi 0 b cross n 1. Now what is mk? So mk is actually, 1 minute, mk is this one, up to this one. So mk is actually, I have represented this one. So this is kind of my kind of my matrix component, okay, with the phase factor. What is the phase factor? What is my phase factor? In color is something else I have to take. Okay. What is my phase factor? This is my phase factor. Correct. Other than that, everything is fine. But remember, what is the advantage? Advantage is that though we are solving a matrix expression, but the matrix dimension is very less. Why? Because S, what is the maximum basis function we can? Maybe S, P, D, F, or one more. So maybe 4 or 5. Okay, for an example, like even you take a 10 or so maximum 10 crossed with 100. So still, it's not that you are solving like billion by billion matrix or million by million matrix. It's a 10 by 10 matrix. It's very easy to solve now. So how many maximum basis for SPDF? So even 5. So I just make it double. So 10. So 10 by 10 is 100 matrix components. It's easy to solve. I'm not asking to solve million by million matrix or 10 to the 22 by 10 to the 22 into. So here, suppose silicon matrix, silicon number of atoms 10 to the 22 per centimeter cube. And if you have a 4 such basis function, you understand the matrix dimension. So 4 into 10 to the power 22 into 10 to the power 22. So 4 into 10 to the power 22 into 4 into 10 to the power 22. So that means 16 into 10 to the power 22 number of matrix we have to solve. It practically impossible. And that is also for one dimension. Now if you have a 2 dimension, that again will increase. So it's a huge matrix, huge. If you consider the basis. So so here actually we are asking only the 10 by maximum 10 by 10, or maybe there are also, I have seen a lot more basis function to correct it, but still it is actually compatible even a laptop. Okay. Now what is MK? So MK, you see this is my MK. So I have given another name. So just to replace this thing, I have given another name, and this is a MK. So MK is HNM B cross B e to the power IK DM DN. So DM and DM, how to deal with DM and DM, that we already studied. Everything is actually we know. Now our main work to find out this part, and it's the same thing we have done earlier. Earlier also we are trying to solve HNM phi m. But here we have to solve HNM by e to the power k dm by this is same. Okay. Only thing is the some matrix component is there with the basis function. So how to compute the matrix? So again our problem. Sorry. Okay, 1 minute. Some problem is there. I have to come back arrow. So you see, this is my problem. So it is a non-Bravia type of thing, so different dimensions. So what we have to do, so we have named it. So the red one is named A, and blue one is named B, A, B, A, and A, B, B, such kind of. And what is the relation between A and B? T. And what is the relation between B of this one to this one? T bar. Simple thing. T1 bar. Now how to find out T and T1 bar? That we have already studied. Just we have to write out the individual component, do some integration, we'll get to know. We'll get to know if we have a proper information. But if you have a proper information, you will get to know T by T1. Correct? Now what else? We have to just make a unit cell. Correct? Then we have to name. So this one we have named N, because you understand now we have to do the summation over M component. And what is the M component? One is nth, one is n minus 1 and n plus 1. Same thing. It is just like a group. So you can, so once you have a group over that, it's kind of periodic form, no? Which is separated by D. That is lattice constant. That means what I'm telling, so here, from here to here, it is separated by that value called D. Sorry, like that. So D value. So from here to here, that is lattice constant. No, same like. So suppose if you consider this is actually kind of one single atom, which we have solved already by our previous example. Same thing we are going to do. Okay, and we have to do the summation from n minus 1, n and n plus 1, correct? Now let's first component. So what we have done, AB and AB, that is AB and AB. Now what is the solution of this one? Do you know this part? Yes, we know. Why? How? Just look at that lecture 1 up here. Now of whatever video lecture I have shared, like if you have a hydrogen atoms from this one and this one, you have a hydrogen atoms. Now two atoms, and now how it form hydrogen molecules. So we did all this exercise, correct? So here you can see like two atoms and it somehow sit together. That means they have a nice balance to each other. So it just you take an example like how it forms hydrogen atom. It's the same thing. So one like hydrogen, one hydrogen and second hydrogen, they sit each other. Just as an example. Now what is the component? We know this component. Okay, so that is nth component here. So because we are doing here, so absolute. So we have a same interdiagonal and the cross diagonal, same thing. Just like a hydrogen atom forms the hydrogen molecule. So now we have to do the summation from other n and n plus 1. So n here, sorry, I have to use different color. Okay, better to use different color. What color I will be using? So let us see. So I have to do n by, I have to use n by n this one and n plus 1 this one. Now, so this is n. So now go for a of n. A of n. A, this is a, no? I think a of n. So this a of n multiplied by a of n plus. So this is again, this what I am saying, a of nth n component this one, and a of this n component has to multiply or has to have things component of a of n plus 1, a by a. So now you see this here a and here a far away from each other, because two wave functions are far away from each other, so definitely the component is 0, no? Like if you consider the wave function here, so this component is 0. So what would be like? So write 0 over here, sorry, 0 over here. So all component. Now just look at that AB. Nth. So this component is actually non-zero component. And why it is T1? Like n is having B, which is multiplying by this one A, correct? And how this one is related to this one, it is just we have already mentioned. So because this is the nearest neighbor, from here to here it is nearest neighbors and they have related T1. Few of many cases that it may be 0 because it is so far away, but let's consider it is T1. Okay, and then we just made. Similarly, we have computed by, and oh, what is the phase factor? So dm minus dn. So from here to here, it is positive d direction. Same way what we have done last time. So I remember here phase factor is 0 because dm minus dn of same position. So that is 0, and exponential to the 0 means it is 1. So what will happen to n minus 1? N of n minus 1, right? And same way, you will get all the component except this part. And you see this part and this part is nothing but transpose. This is a great thing that will work in later, how to utilize. So this is the whole way that we have managed our matrix. Then you are done. Then we have to matrix summation. So epsilon. So this is actually epsilon. Then T plus T1 e to the power ikd. Similarly, another one T plus T1 e to the power plus ikd and an epsilon. Right? It's a matrix summation. Now here actually one thing you can see, as I told you, just this, what is the relation from here to here? This is actually complex conjugate of this component, no? Minus ikd, and this is actually plus ikd. So this is actually, this is an imaginary part. So this is a complex conjugate of this one. So kindly consider those things. Now what is the eigenvalues of this matrix? So you know, so you can calculate the eigenvalues. So but you know what is the rules of eigenvalues? Suppose we have a 2 cross 2 matrix, and if the diagonal is same and another diagonal is actually complex conjugate of each other, this one to this one, so what is the eigenvalues of these things? Epsilon plus minus the magnitude of this one. Okay, now what is the magnitude of this one? You know how to calculate the magnitude of this one, like complex conjugate part. So this one multiply this one under root, right? This is the magnitude. So that same thing we have done, epsilon plus minus, this is the magnitude. And if you go and if you do further manipulation, you will get 2t bar cos kd half. So see, it is actually my EK diagram of a multiple basis function. That is the fantastic way to calculate my basis functions. Okay, multiple basis function. If you have a multiple basis function, you can easily calculate in this phenomenon. Okay, so now how it looks. So if you take epsilon plus this one, you will get this part. If you take epsilon minus or cos kd, you will get this one. And what is the maximum value? So epsilon plus t square t1 square by 2t by t bar. So there is a 2t t bar, which comes like this one. And similarly, what is the minimum value of this one, and similar maximum. So this is the way that we can easily get easily calculate my uh, what is called that basis. If you have a multiple basis function, you can easily calculate those things, and you will get to know all these results nicely. Okay. Now the question sometimes people. Okay. No, fine. Now the next question that I'm going to ask you, like this is fine. I hope you understood the problem and the solution, how to tackle it. Now my question is like, homework is this one. Compute the equilation of 2D lattice shown in figure below. This, because I have done one dimensional crystal part, so I am asking you to do one more homework of this type of 2-dimensional crystal lattice. Okay. So thank you. Thank you for listening it, and I hope you understood all these things. If you have any doubt on it, so you can discuss with me. The better you discuss among yourselves, like you have a good friendship, you have good friends over there, and definitely when you come back, we'll have another discussion round on these things, and hopefully it's clear. Okay, thank you. So next day, what we'll do? Next day, I'll try, either I'll come up with a particular application like graphene or carbon nanotube, or I'll come with directly how to find out density of states out of that. Okay, whatever. Thank you.